We're doing chapter 16 questions, practice questions. You can find the practice questions in the course management form, and you can find the actual problems in the textbook. And yeah, that's it pretty much. So let's get started, I guess. So like I said, I don't know if you heard me because like people were still joining. So I looked through a couple of the questions. The first question I don't know how to do. The other ones I do know how to do, but the first one I don't. I think it's because it's about these earthquake things, I guess. Oh, sorry, I'll take a better screenshot than that. It's my fault that they look like that. And I don't even remember him ever talking about earthquakes. Like, I mean, okay, a little bit, like he mentioned them, but like not like some terminology. But okay, I think we'll probably still be able to figure it out. So a seismograph station receives S and P waves from an earthquake separated by that many seconds. Okay, assume the waves have traveled over the same path at speeds of that and that. Find the distance from the seismograph to the focus of the earthquake. So essentially what's happening is that this is like a top-down view of the land. Okay, this is the focus of the earthquake, right? Or the focus of the, what did it say? Focus of the quake. And right here we have a seismograph. Okay, so whenever an earthquake happens, one wave goes down, I guess called the S wave, and another wave goes down, I guess called the P waves, and they go at different speeds. So somehow, so the V of the S is 4.5, or I'll say 4,500 meters per second, and the V of the P wave is 7,800 meters per second. The delta t between the times is 17.3 seconds. So the wave goes out from here, but all we really care about is that it goes at this speed from here to here. So the time, what are we looking at? The distance. We're looking for this radius here, the distance traveled. And so the waves come out in these kind of shells. I guess maybe we do care about that. The waves come out in these kind of shells. Comes out in these kind of shells. And, but how do we use that to help us find the distance here that it traveled? Yeah, I don't know. I also didn't hear him ever talk about earthquakes, so I feel like just skipping this question because I don't know how to do it. But does anybody know how to do it? Does anybody have an idea?
One is 17.3 seconds faster.
Well, not necessarily, because the S and P waves, they don't. No, I guess they do happen at the same time.
Yeah, it's just separated by 17.3 seconds, so I think you just use velocity equals displacement over time, or times time to time. Displacement equals
Like
velocity.
velocity equals distance over time. So this it will get me the distance, but
Yeah. So one time is t, and the other is t plus 17.3.
oh, okay. And that's the time it took to get there for the first. So t is the time it takes. T is the time. Time it takes for the S wave to arrive. Okay, so t times for the S wave, so that's 4,500 equals the distance, and then I have another equation which is t plus 17.3. Oh, okay, that makes sense. T plus 17.3 times the second velocity, 7,800 equals d, and just solve for d. Yeah, I guess so. So
I'm guessing.
yeah, I guess so. Sure. Let's rearrange. Well, this is equivalent to t equals d over 4,500. So d over 4,500 plus 17.3. Well, I guess you know what, I'll do it like this. Okay, no. Plus 17.3 times 7,800 equals d. So 7800 d over 4500 plus 17.3 times 7800 equals d. Times 7800 equals d. And then it'll be 7800 d over, well, 78 over 45 d minus d equals negative 17.3 times 7800. And so then d equals minus 17.3 times 7,800 over 78 over 45 minus 1. Let's see if that works.
Can you spell it for a second?
Yeah.
A little higher, please.
A little higher.
Yeah.
Is that good?
There we go. I think the time for the velocity p is just t, and velocity s is t plus 17, because the faster velocity would get there faster than the 4500 velocity.
So this t is the time it takes for
P wave, I think.
because it's the faster wave.
Yeah. And the other one is t plus, because it takes extra 17.3 seconds.
Oh, and they come. Oh, okay, and they happen at the same time.
Yeah.
They like
I assume.
come from the same time. Okay, so the only difference is that this is just p.
Yeah.
And that's the only difference. Okay. So then, but yeah, it doesn't change this answer. So it's 78 over 45 minus 1. Well, I get a negative number, but let's see if it's the right negative number. D equals, this is in meters. Yeah, so I get 184 kilometers. But I got that negative for some reason. That is the answer, though, so I'll just go with it. Maybe that's not supposed to be negative. Maybe that's supposed to be a minus. I'm not sure, but we got the right value, so I'll just go with that. Okay, good. Well, I'm happy to figure that out. Let's take a look at the next one. Number 5. So number 5 is when a particular wire is vibrating with a frequency of 4 hertz. So frequency equals 4 hertz. A transverse wave of length, 60 centimeters. Oh, sorry, of wavelength, 60 centimeters. Wavelength equals 0.6 meters, right? Is produced. Determine the speed of waves along the wire. Speed of waves along the wire. I guess that just means the actual wave speed. So, yeah, not the speed of any given part. They would be more specific. So we can just use the fact that V equals lambda F for this. So that's just 0.6 times 4, which is 2.4. So the answer for 5, yes, 2.4 meters per second. And there you go. Okay, that was easy. Let's try the next one. So number 7. So number 7 is here. Consider the sinusoidal wave of example 16.2. Well, let's find 16.2. Example 16.2. This is section 16.2. No, probably need example 16.2. Okay. Oh, I think it gives us the wave function. Okay, so all 16.2 was it gave you the parameters and you made the function out of that. So that's like, this was like in the, well, like practicing. It was in literally chapter 16.2, so kind of early on. so we don't actually need anything from the question. I don't think. Let's see. Okay, where x and y are in meters and t is in seconds, at a certain instant, let point A be at the origin and point B be the closest point to A along the x-axis where the wave is 60 degrees out of phase with A. What is the coordinate of B? Okay, I don't know why this is in degrees, so that's pi over 3. And then, so we have this function. Let point A be the origin. Does this pass through the origin? I don't think so. It might. 0. This is 0. X equals 0, t equals 0. No, that wouldn't pass through the origin. So point A be at the origin, point B closest point on the axis where 60 degrees. What is the coordinate of B? Well, probably a graph would be helpful for this. We just want to be 60 degrees out of phase with A. So we just want to add pi over 3 in here. That would make us the closest point to A along the x-axis where the wave, and well, I guess I would want to subtract, or it doesn't matter actually. Yeah, it doesn't matter. I think we just want to, that's what I would do. And I would need the height of the graph, I guess is what I want, at point B. Yeah. Or the y value, I guess, at that point. Let's try it, I guess. All I'm going to do, I'm just going to see, what's the y value for 0.150 cos of, well, if it's at the origin, so we want to take the origin, which is just 0. This is 0, 0. And I'm just going to, well, I guess I'll add pi over 3. So 0.15 times cosine of pi over 3, which is 0.075, which is not the answer. Let's see if, well, I mean, subtracting won't do anything. But I will try it anyways in hopes that it does. It does not. Because it's even, so we're at the origin. So x and t are both 0. Maybe, yeah. And I just want to move 60 degrees. 60 degrees is pi over 3, I'm pretty sure. Yeah, it is. So let me make sure I understand what the question's even asking for. So let me make a Desmos graph. Oh wait, no. We don't know. I don't know what's loading on my computer, but something. Anybody got any ideas? 1.15. I can't even. I would have to set one of them to 0, either x or t.
I think it's x to 0.
Yeah, I think you're right.
Yeah, x to 0?
Yeah, because it says B is well, it doesn't explicitly say B is at the origin. It just says A is at the origin.
Yeah.
So I'd imagine B is either a little bit forward or backward along the x-axis, meaning some time has passed before it gets to point B.
Point B, yeah. What is the coordinate of B? What coordinate, though? It wants the x coordinate of B, I guess?
I think it wants both the x and y.
Well, no, the answer is just...
Well, the x would be 0.
The answer
well, not
is
0.
just
Sorry.
a single number.
6.37. Oh.
I think we already get one point, like x probably x, because it has to be in line with A, right? And A is the origin.
Mm-hmm.
And it has to be the closest point to A.
Yeah, I guess so, yeah. But Okay, I guess I see.
I guess I see. Sure.
Someone's got major echo
Someone's got major echo
on there.
on there.
We're gonna make x equals to 0 because that's like the only logical thing, and it's going to be, so b is going to be some time. We have to find t, I think. We have to make x equals 0 and find t, I think.
But the answer in the book is the
The
distance.
book is the distance.
It's in centimeters.
It's in centimeters.
Well, it is a distance because a is at the origin, so b is going to be like basically a distance, right? From
Yeah,
a.
further down the x-axis.
X-axis.
Yeah. So if you find the point B, it's basically going to be the distance from A to B.
Oh, I guess the height would also be 0.
Would also be 0.
And I just want to do 15.7.
15.7.
Hold on.
Yeah, just
Hold
add
on.
the fifth constant to that original
Yeah.
equation.
Yeah.
Okay, let's try this. So I'm just looking for when does cos of 15.7x plus pi over 3 equal 0. Okay. So I can say, well, cos inverse of 0, the first one, I guess I'll just choose the first one, is pi over 2. So 15.7x
0.7x plus pi over 3.
What's the x-axis here? Isn't x-axis time?
No, the x-axis would just be the x value.
Would just be the x value.
I'm confused. I'm just asking. Like, if we were to graph that thing, how would we graph it?
You'd have to graph it in 3D or
In
set,
3D
or set a value of t
or set a value of t or set a value of x.
Okay, yeah, I guess that makes sense.
So 15.7x equals pi over 2 minus pi over 3 divided by 15.7. So will this get the answer? Pi over 2 minus pi over 3 over 15.7, and not the answer. I get 0.033. 334. So is there another cos inverse I'm supposed to be using? I don't really know why. I would need to use a different cos inverse. It seems like I should. I don't know what it means. What is the coordinate of B? What coordinate though? I guess the x coordinate. Maybe the t coordinate? Let's try with the t coordinate instead. This will be negative 50.3 t. The height is still 0. So this is negative 50.3 t, negative 50.3 t, t, negative 50.3. Let's see if that makes a difference. I'll get a negative number, I know, out of it, but no, still not the answer. So at a certain instant, that a along the x-axis. So we're looking for an x value for sure, where the wave is 60 degrees out of phase with A. Yeah, so we want to be 60 degrees further along. Is the problem that I'm adding here? Should I be subtracting? Maybe I should be subtracting and put this back to x. So put that back to x, because I think x makes more sense. So this is 15.7x, 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 and this is 15.7x. Will this give me the answer? What was the answer in the book? No. So, yeah, we just have we're setting a value to 0. I guess we're setting, oh yeah, at a certain instant. Okay, so they say at a certain instant. That means t, we'll just choose a value for t, I guess. We'll just choose t equals 0. Let A be at the origin and point B be the closest point to A along the x-axis. Well, hold on. We don't actually know what t is. We then have to solve it in terms of t. That doesn't make sense. Okay, I don't know. Does anybody have any ideas, or potentially Slater? Let's see. Chapter 16. Problem. Oh, it's just not the same question. Yeah, it's just not, Slater just doesn't have the same question. At least maybe I'm in the wrong edition. But okay. Well, I don't know. If anybody has any ideas, let me know. Otherwise, I'm gonna just move on. But I'll put a question mark here. Okay, I guess I'm gonna move on. Let's see the next one.
Sorry.
Yeah.
What's the answer for 7?
6.66, I think, or 6.67. Yeah, centimeters. So, be clear here. Yeah, I'll write it. Answer is 6.67 centimeters. Well, plus or minus that, which makes sense because you'd be able to go in either direction there. Oh no, not necessarily, but yeah, no, that would make sense because this is 0 and we're just seeing the distance from, yeah, so then this makes sense to be plus or minus. This is half of it, what I got here, which isn't actually the value here, which isn't actually that value, but when I got that answer, it was half of it, but if that was in meters, to be clear, but yeah. Okay, next one is, we just did 7, so 8. Okay, sinusoidal wave with traveling in the negative x direction to the left has an amplitude of 0.2 meters, a wavelength of 0.35 meters, and a frequency of 12 hertz. The transverse position of an element of the medium, so y of 0, 0 equals -3, or -0.03. The element has a positive velocity here, so v of 0, 0 is greater than 0. We wish to find an expression for the wave function describing this wave. Okay, sketch the wave at t equals 0. Okay, well, at t equals 0, it will look like, I hate when it moves like that. At t equals 0, we will have, it's a negative position, and it's moving upwards. So it will kind of look like, I don't know, like this, I guess. Right? It will kind of look like that at t equals 0. If that's the t-axis, and that's the y-axis. So find the angular wave number k from wavelength. The angular wave number? Angular wave number. First time I heard that.
The W.
Yeah.
Yeah.
Which is just the angular frequency.
Angular wave number is k.
Wait, what?
Angular wave number is k.
But
I think they just made K, sorry. Yeah.
okay, I guess they just.
Okay,
yeah,
I guess they just.
Okay. So well, omega equals square root of k over m. We don't know any mass, right? So hopefully that will somehow cancel. Let's see. Omega is what's another expression for omega?
2 pi f.
2 pi f, yes. So omega is also 2 pi f, so we can say 2 pi f equals the square root of k over m. So 4 pi squared f squared equals k over m, and just multiply by m there. So that's k. And now we need to find, yeah.
Oh, are we looking for omega or k?
K. We're looking for k, I'm pretty sure.
Oh, it's 2 pi over wavelength.
2 pi over lambda.
Yes, I am overcomplicating it. So, yes, the k value. Oh, yeah. Okay. I was thinking the k like a spring constant, but no, this is just part of the equation. Yeah. So k is just 2 pi over lambda. Yeah. 2 pi over lambda. So that's 2 pi over 0.35. So that's 2 pi over 0.35, which is 17.95 meters. Or not meters. 17.95 per meter, I guess. Yeah. So meters to the negative 1. And let's see if that's right for 9, I think. What are we doing? 8, which I don't have the answers for, so we'll just go for it. Then we need B, find the angular wave. No, that's already it. Find the period t from the frequency. Okay, so if the frequency is 12, the period is 1 over the frequency, so 1 over 12. Okay, so period is 1 over 12 seconds. Okay, then find the angular frequency omega, and okay, so let's start with omega. Omega, like we said just now, is 2 pi times the frequency, so that's 2 pi times 12, was it? Yep, 12, so that's 24 pi. Okay, 24 pi, right there. I'll actually write the answers, like the sections here. So this was part A, this was part B, this was part C, and this is part D, and then part E is the wave speed, V. Okay, so V is, we can write that as lambda f. Yeah, V equals lambda f. So lambda was 0.35, and the frequency was 12. So 0.35 times 12 is 4.2 meters per second. And is that everything? Nope. From the information about t equals 0, find the phase constant. Write an expression for the wave function y, and then write an expression for the wave function as a function of x and t. Okay. So, I mean, essentially we're doing g, right? To do f, we kind of have to write an equation. So let's write an equation in general. What would it be? So y equals, we don't know it's a, I was just about to say, we don't know it's a sinusoidal wave. We do know it's a sinusoidal wave. So I will say, okay, so in general, a sinusoidal wave as a function of x and t is, I have it here, a sine kx minus omega t plus phi. Okay, what do we know? Well, we know A is 0.2. 0.2. We know K, we've solved for K, was 17.95. Right? And then omega, we solved as 24 pi. Times t plus phi. This is y of xt. So now, well, we'll use the information we know at t equals 0. So what's the information we know at t equals 0? Well, the position of an element at t equals 0, x equals 0, of the x equals 0 element at t equals 0 is that. So we can say, what was it? It was equal to negative 0.03, right? So negative 0.03 equals 0.2 sine of phi, because it's 0, 0 for the rest of them. Right, so it will be equals sine phi. Okay, so now we take the sine inverse, and yeah, let's just take this first. Let's get the first sine inverse. So sine inverse of negative 0.03 over 0.2 negative 0.03 over 0.2. Yeah, that makes sense. So I got my first phi equals negative 0.1506. I'll be a little more specific. And my other solution is sine is negative here and here. So I got this solution, I'm pretty sure. So that I got this solution, which is that negative 0.15. Pretty sure, yeah. So yeah, which I'll turn that into. I'll do 2 pi minus that number. Right. So 2 pi minus that is, or no, it should have been 2 pi plus that. Yes. Oops. Okay, hold on.
People are asking me if you can speak louder. They can barely hear you.
Oh, you can't hear me?
I can hear you, but people are telling me if you can speak louder. They said they can't hear you in the recordings.
Oh, in the recordings for the thing? Well,
yeah.
Okay. I'll turn up my mic audio then. Let's see if that fixes it. Well, thank you. There. I turned up the mic audio a little bit, so hopefully you can hear.
Okay. Thanks.
So negative 0.03 over 0.2. I lost the value because I have to do 2 pi plus this number. Okay, so my first solution is 6.1326, and then my second solution, which is this angle, right? And then I want to get this angle in here, so I need to do pi plus 0.1506, right? Because 0.1506 is this little angle here, which is the same as the reference angle here, right? That's 0.1506. And then, so to get it in here, right? To get it in here, we need to do the, like, this, to get this number, right? That's this angle like that. I did 2 pi minus the angle, minus this angle. And then to get it in here, I do pi plus this angle. To get it in this quadrant, I do pi plus the angle. Okay, so that's gonna be that. So our second solution, first one is 2, 6. I know I'm writing it in 3 different colors now, but then pi plus 0.1506 is 3.292. Okay, well, I guess I'll put another decimal place. So now that we have these two values for phi, we have to decide which one's the right one. Well, we want the velocity to be positive at that time. So one way we could do this, think for a second. Do we have the velocities like this? No. Okay. Well, one thing we could do, yeah, how would that change it? Okay, let me rewrite this equation down here so that I have it. Well, I think one way to do it is to graph it. Oh no, we can't graph it. Hold on, there's 2 variables. I can't do it in Desmos. Well, I can set.
Wait, did they say the velocity is positive?
Yeah, they said the velocity is positive. They did say the velocity is positive, or let's just check. The element has a positive velocity here, yeah. Right? So essentially what's happening is that I have this situation going on here. If I make just a set value for t, I'll just say t equals 0, right? Then all we have is 0, well, I have to look at the screen because I don't know the numbers. 0.2 sine of 17.95 x plus phi. Okay, now what's phi? So let's try the first one. I'll try 6.1326. So if we look at the graph, I tried the first one. Well, it has a positive slope here, right? So this looks like it's going to be the answer to me. Our other option was 3.2922. So 2922, and you see here it has a negative slope at 0. Right, so 6.1326 is our phi. Right, so phi equals 6.1326. This one is not what we want because of this criteria that was put here. So it must be this one. So we chose this. Okay, so there's that. Then we have our thing, and so I can just rewrite the equation again, but just putting phi in there. So this is just going to be plus 6.1326. And there you go. Let's check that answer. This was number what? Oh, number 8 again, which I don't have. So we'll just have to live with it. But yeah, this makes sense. That you need the one with the positive slope. Okay,
Can you quickly go over that part again? How you got the phase constant?
Yeah, how did I get the phase constants, or how did I choose one? Which one are you asking? Or both? I can explain.
Both, please.
Okay, so to get the phase constants, okay, so does this make sense, how I got this equation?
Where does negative 0.03 come from?
That's saying the transverse position of an element in the medium at t equals 0, x equals 0 is y equals negative 3 centimeters. So I'm doing everything in meters.
Okay, yeah.
Right. So I wrote this equation then, which rearranges to that. Okay, so now what are my values for phi? Well, if I just stick it into my calculator, I get this. Okay, I get this. And we want the positive of that. That's the reference angle. So so I'll say the reference angle is 0.1506. So now I have to figure out what are my actual angles that are my solutions to this sine. Well, I want sine to be negative, right? Sine theta is sine phi is a negative number. So where is sine negative? Well, it's negative in these two quadrants, and my reference angle is whatever, some angle like that, right? So I'll say R for reference angle. So I want to move that reference angle into the fourth quadrant and the third quadrant. So to move it to the fourth quadrant, right, let's start with that. To move it to the fourth quadrant, I take 2 pi, and then I subtract the reference angle. And that'll move it here. I'm doing everything with one color. Probably shouldn't. So 2 pi minus the reference angle, and that'll move the reference angle into this position right there. Right? So it's not the reference angle anymore, but it's the, whatever angle. So that's this first one. 2 pi minus the reference angle is this. And then to move it into the third quadrant, right, because that's the other place where sine is negative, I do, you do pi plus the reference angle. And that gets me this number. Okay, so there's my two values of phi. Now we have to decide which one is it. Well, in only one of them, I have a positive slope. Positive slope. Because look here, this is using the 3.2922, and you can see at the x equals 0 element at t equals 0, it has a negative slope, a negative velocity at that time. But then if I use the 6 point something I forget, but you can see the effect is that it's a positive slope here, right? You can see there's a positive slope, and that's what we want. We want a positive velocity, so this is the only answer that it could be. 6.1326. And then I just put it into the equation, and there we go.
Shouldn't the 24 pi be positive because the velocity was negative?
The 24 pi
For the wave.
here?
Yeah,
oh, and we actually, hold on, we are actually missing something. It's moving in the negative x direction. This is why it should be negative. It says it's moving in the negative x direction to the left. So, yes, it should be. It should be a positive number. Didn't affect anything in our solutions because we set t equal to 0. Right? But, yeah. So that only controls if it's moving left or right. So negative is to the right and positive is to the left. Okay, so does that make sense?
Isn't the equation of the line moving in the negative x direction supposed to... Okay, yeah, never mind, you changed it now.
You're good? Okay.
Yeah, that's fine.
Okay. So So if there's no more questions, I'll move on to number 9.
Is the phase constant negative or positive?
It's positive.
It's positive. Positive.
Okay. Oh yeah. Okay. So when we put it in the equation, is it negative? Do we put minus the phase constant?
No, it's positive phase
No,
constant.
it's positive phase constant.
Put it here.
Put it here.
Because that's the formula.
Because that's the formula from here.
Okay, no. Okay, so
Wait.
yeah.
Here's a question. Why is it plus 24 pi again?
Because this just controls if you're moving left or right, right? This value here. So if it's plus, that means that the graph is being shifted this way, right? And if it's negative, then the graph is being shifted that way.
Oh, okay, I get it.
As t moves forward, just to be clear, as t moves forward.
Okay.
It's bigger, right? Yeah. Okay, so there's question 8. Question 9. Write the expression for y as a function of x and t in SI units for the sinusoidal wave traveling along a rope in the negative x direction. So we're going to use the positive sign there again. With the following characteristics. Okay, A equals 0.08 meters, but I'll leave off the units. I'll just put everything in meters. Lambda is 0.8 meters. Frequency is 3. Okay. Y of 0t equals 0. What? Y of 0t equals 0 at t equals 0. So they mean y of 0, 0. Okay, I think they just mean y of 0, 0. I don't know why they said it like that, but okay. Sure. Okay, so write an expression now for this. Okay, so we want y of x comma t equals a sine, what was it, kx, yep, kx plus omega t plus phi. Okay. Well, we got to find all our numbers. So a we have. K is just 2 pi over lambda. So K is 2 pi over lambda. So that's 2 pi over 0.8. So that is 7.85 or 854, I guess. I'll do one more spot. That's K. Now we need omega. So omega is 2 pi over the, or 2 pi times the frequency. Yeah, 2 pi times the frequency. So omega is 2 pi times, I'll do times the frequency, which is 2 pi times 3, which is 6 pi, right? So, and I'll leave that one. You know what, since I left that as a, I'll leave this one also as just 5 pi over 2. Okay, then we have everything we need, except just need to use this to figure out the 0, 0. So y of xt equals, a was 0.08, sine of k was 5 pi over 2x plus 6 pi t plus phi is our function. Now we know that y of 0, 0 equals 0. So 0 equals 0.08 sine of 5 pi over 2x plus 6. Oh, no, sorry. Just phi there. That's all that's there. So we're looking for where does sine phi equal 0. So sine phi equals 0 at 0, pi, and 2 pi, right? So, well, it could be any of them, I guess. So let's just say 0. Let's just say it's 0. So phi equals 0. Oh, okay, too confusing to write a circle like that, so phi equals 0. Right, it could be pi or whatever, but we don't have more information, so So write the expression for y as a function of x and t for the wave in part A, assuming that y of x0 equals 0 at the point 10 centimeters. I don't know why they write it like that. Okay, I guess they write it like that here to confuse you a little bit with the units, but that's, I guess, it. So, let's check our answer for this one. This was number 9. So 0.08 sine 2.5 pi x plus 6 pi t and phase constant 0. Okay, we're good with that. So this is part B. So same wave, is just a different phase constant. So I'll write the wave again here. I'll just copy and paste this. It's the same wave. The only thing that's changing is that now instead of at y of 0, 0 being 0, y of 0.0, it was, what was it, 1 centimeter? No, it was 10 centimeters, yeah. Y of 0.10 equals 0, right? Assuming y of x0, like that, assuming y of x0 equals 0 at the point x equals 10 centimeters. So y of 0.1 meters, 0 equals 0. That's what I'm saying. This is what we get from the question. So let's try that. So 0 equals 0.08 sine of 5 pi over 2 times 0.1 plus phi. Okay, and now we need to solve for phi. So 0 equals sine 5 pi, well, this is 0.1 is 1 over 10. So 5, this is just pi over 4. Right? Yeah, pi over 4 plus phi. Okay, now again, where does sine equal 0? Well, when this equals 0, right? So when pi over 4 plus phi equals 0, so we can say that phi, vertical line, phi equals negative pi over 4. And yes, that is the answer. So the answer is this equation, but with just with that, well, that put in for phi. And since they don't tell us any kind of information about like velocities and stuff like that, you don't have to worry about other possible solutions. This is just one of them. There is technically a few more. Well, there's infinitely many, but there's a few more that are notable. But yeah. Okay, so are we good with that? Question 9, any questions? Okay, I think we're good. I'll move on to number 11. So for number 11, the transverse waves travel with a speed of with a speed of 20 meters per second on a string under tension of 6 newtons. What tension is required for a wave speed of 6 meters per second on the same string? Okay, so all we need to do is to have this equation. So V equals the square root of the tension over the length, the density. Is that what it's called? Mass per length? Yeah, or not length density. I forget what it's called, but mu, which will look like a K. So we know that 20 equals square root of 6 over K. So we can just solve for K and then just solve for T again with the same equation. So this will be 400, right? 400 equals 6 over K. So K equals 6 over 400, right? Which is 3 over 200, which is some number. And then that's our K value. So now I can just go here and solve. I can take the same equation. V equals the square root of T over K. And we're looking for what tension is required to make this speed with the same rope. So the same, that is actually mu. I've just been calling it K this whole time. So my own writing is screwing me up here. But yeah, for the same mu, what tension is required? So we just say, I'll just say 30 squared equals T over mu. So well, then I can just multiply. So it's going to be 3 over 200 times 900 equals the tension. The tension. So there. 3/2 of 9 is 13.5. And let's check that. 13.5. We're good. Okay. Hopefully that question's good. Just let me know if there's any questions. Oh yeah, people are DMing me, so let me take a look if people have any questions, and I will answer. Okay, some things I'll take a look at after. Okay, we're good. So next we have, that was question 11, so question 13 is next. Question 13 is here. Whoop, it's a pulley question, so let's take a look. So tension is maintained in a string, as in this figure. The observed wave speed is that when the suspended mass when the mass is, the wave speed is that when the suspended mass is that, okay. The wave speed is in what's causing, okay, let's see. What is the mass per unit length of the string? Okay, well, actually, we can do this. So, well, what forces are acting on this block here? Well, we have a force of gravity going down, and we have a force of the force of tension going up. So what's the sum of the forces in the y direction? Well, it's equal to 0, right? So if I define that as up, so it's going to be the force of tension minus the force of gravity equals 0. So the force of tension is equal to the force of gravity. So now we know that the force of tension in the rope is mg. And we're looking for what's the mass per unit length of string. Well, we can use the same formula as last time. Tension over the mass per unit length. And just solve for mass per unit length because we know tension is that, right? So I can just say v squared equals t over mu, and then mu equals t over v squared. So mg over v squared, so that's mass was 3 times 9.81 over v squared, so 24 squared. 3 times 9.81 over 24 squared. So I get mu is 0.05511. Something per something, whatever the units are. This is question what? 13? Yeah. 0.051 kilograms per meter. Yeah, that makes sense. Kilograms per meter. Okay, and then what is the wave speed when the suspended mass is that? Okay, not bad. Well, we do this essentially the same thing. We say, we take this equation, right? Well, the wave speed is v equals the square root of the tension over the mass density or whatever, the string density. So we say, okay, well, the tension is mg, and we want to divide that by mu, so that's the square root of 3 times, oh no, sorry, when the mass is 2. 2 times 9.81 over 0.0511. So this is square root of 2 times 9.81 over 0.0511. Yep, so I got 19.6 meters per second. And that is the answer. Okay, any questions about this question? Okay. I think we're good. Let's move on then. I'll be taking a break in about 10 minutes. Okay, guys? So 7:15. Take a break. So transverse pulses travel with a speed of that along a taut copper wire whose diameter is that. What is the tension in the wire? The density of copper is that. Okay. So the wave speed is 200. Okay. Taut copper wire whose diameter, what is the tension? Okay, so we know that V equals this. This is, again, the thing we're using. Okay, we need to figure out what this is, right? So mu is kilograms per meter. Yeah, kilograms per meter. So in 1 meter, so we have the rod here, right? If we have, well, it's a wire, but let's just say it's a rod, really. If you zoom in, right? So we have the rod here. Diameter is, okay, to convert that to meters, I'm going to move 1, 2, 3. So it's going to be 0.00000, no, 0015 meters, right? Because I need 1,000 of those to make a meter. Yeah, okay, good. So that's the diameter, okay? And now we want to ask ourselves, how much does this weigh? Well, we need the volume of this, right? So this is a 1 meter length. We need the volume of this, and then we just multiply, oh, I guess in centimeters cubed, that's what we want, so I guess we'll do that. So in centimeters, this will go back 2 spaces. So it'll be 0.15 centimeters, and this is 100 centimeters. Okay. So, yeah, that makes sense. So now to find the volume of it, well, how do you find the volume of a cylinder? It's the area of the face, pi r squared, right, times the length of it, which in this case is, well, times the length of it. So that's the volume. So pi 0.15 over 2 squared times 1, right? That'll be the volume. Pi times 0.15 over 2 squared times 1. Okay, so the volume is 0.0177 centimeters cubed. And now I want to know how much that weighs, right? So, well, we have the density. So I just multiply it, right? I just take the density. So mass equals the density times the volume, right?
Yo, sorry, I got a quick question. So
Yeah.
where were you told the length of the rod?
I want to know the mass per meter. So I'm saying this is 1 meter.
Oh, per meter. Okay. Yeah.
Right? I'm
So,
telling
yeah.
you, like, I'm choosing that to be 1 meter.
All right.
Okay, so then, yeah, then we just take the density. So that's 0.92, not 0.2, 8.92. I don't know why I said 0. 8.92 times the volume, which was 0.0177. So that's going to be 8.92 times 0.0177. So I get a mass of 0.157884. A mass? No. A mass. Okay, and then so from that, we can find that the mu is the mass over 1. So the mu is 0.157884 kilograms per meter. Yeah.
Adam, quick question.
No,
Sorry to
hold on.
interrupt.
So I made a mistake here, but yes, you ask your question. Sorry.
I'm sorry. Is it multiplied by 1 for the volume? Is it multiplied by 1 or by 100?
It is multiplied by 100. You're right, which is exactly the mistake I made. So this would be cool. 1, 2, right? No, hold on. 1, 2. Wait, what am I doing? This. Let me just type it in again. I don't want to make a stupid mistake. So 0.15 over 2 times 100. So I get, yeah, that's what I thought. So this would be, 0. And then this would be, wait, how did I get a different number? Just by multiplying by 100. No, I didn't get a different number. I'm looking at the wrong thing. Yeah, that makes sense. So it's going to be
here.
1.76. Someone's got their mic on. Okay, I think we're good. Okay, so let's take, sorry, someone just said something about question 7, so maybe we'll go back to it and see if it works. Yeah, so this is going to be that. So we take that, 1.767 centimeters cubed. So this is going to be in grams per centimeter cubed. No. This is just going to be in grams. And then, but it's still off by 10, right? So I take this and I multiply it by 8.92. So yeah, I should get 15 point that. Yeah. So that's the amount of grams per, so I can say this is the amount of grams per meter. That's okay saying that. 15 point that. And then I just want to make that kilograms. So I divide by 1,000. 1, 2, 3, 0.0. So it's going to be mu is 0.0157884. Okay. That's mu. What is the tension? Well, we can just take this equation and rearrange for tension. So mu times v squared equals tension. So I will take that equation, put it here. So I can just take mu, 0.0157884, multiply it by v squared, so 200 squared, and that should give us the tension. Sorry, did I say this wrong again? No, I did say this wrong again. I thought I had the decimal in the wrong spot again, but no, it's not. So then I just take 0.0157884 times 200 squared. So I got the tension is 631.5 newtons. And this was question 14, which does not have an answer in the book. Hopefully that's right. So any questions?
I have a question.
Yeah.
For the volume, for the length, the L, where did the 100 come from?
Well, I'm choosing this because the mu is kilograms per meter, right? So this is 100 centimeters, which is the same thing as a meter, right? So I just chose the length of the bar or the length of the wire to be 1 meter because I want to know how much that weighs.
Oh,
in order
okay,
to find
got it.
Right? And so I wanted in centimeters though.
I wanted in centimeters though, so I put 100 centimeters.
All right, thank you.
All right, thank you.
Yeah. Can you say that again?
Can you say that again? Someone there?
The mass per mu thing, you could have also just multiplied the density by the cross-sectional area, apparently.
Yeah, I was gonna say I did that too, and I
I
got
did
the
that
same
too, and I
answer.
got the same answer. Okay.
Yeah, that's very similar.
That's very similar thing to do. Yeah.
This is kind of confusing.
Yeah. So I guess is there the formula somewhere that I don't have?
You just multiply the density by pi r squared over 4. Pi r squared divided by 4.
Y divided by 4.
I divide by 4.
You have to do the cross-sectional area.
Yes, you just do pi r squared.
Pi r squared.
Yeah.
And then
you
once you have that cross-sectional area, you can solve for the mu. And it's the same mu as you found.
I searched it up and it said pi r squared over 4.
I don't know why it'd be over 4 though.
Because the circle.
The cross-sectional area is a circle, and that's just pi r squared.
Pi r squared.
Yeah, I'm not sure.
Not sure. Yeah.
I just thought it was because it's a cylinder, and wasn't it something like that for a cylinder? Yeah, okay, I don't know. I guess pi r squared works too.
Yeah. The units also work out on that.
Units
right?
also
Because
work
if we
out on
find
that,
the
right? Because if
cross-sectional
we find the
area-
cross-sectional area.
We find the cross-sectional
We find the cross-sectional area.
area equals. So the area is going to be in centimeters squared. We're multiplying that by grams per
centimeter cubed.
So it's going to be grams.
So it's going to be grams per centimeter.
Which is essentially what we want.
I dropped how I did it with the cross-sectional area.
area.
Hold on. Whoever it is with the echo, could they mute their microphone? Okay. Okay, we're good now. So yes, you said homework help. Let's see. Yeah. Yeah. Cross section bar squared. Wait, you did 0.015? Wait, how did you get the right? Wait, the arc radius is not 0.0.
Yeah, sorry, I didn't write that I divided it by 2. That's the diameter I divided it.
Okay, you did divide it by 2. Okay. And then okay, so then that's the cross sectional area, and then mass per length. You got that many kilograms per meter. Wait, the cross.
Yeah, so I just converted the grams per cubic centimeter into kilograms per cubic meter, and then the units cancel out because the cross section.
How did you get 8.92? That you did that by multiplying your cross section by the density?
So I got the 8.92 is given as the density, right?
Oh, yeah.
And then I just converted that to kilograms per cubic meter, and then if you multiply that by the cross-sectional area, which is meters squared, you get your mu, which is kilograms per meter. I did it. It's just like your method.
Yeah, it's the same thing. So you can take the cross-sectional area, right, the area of the circle, and then multiply that by the density of the copper. Just make sure your units work out, and that'll work.
So just to clarify, so if you were to convert the density of the copper wire into kilograms per meter squared or cubed, could you multiply by the surface area of the copper rod as well, and then
the surface
you'll
area?
cancel that? Yeah, because it's meters squared. That's what I'm thinking. So if you multiply it, then you're just left with meters in the denominator. Could that also work?
I don't think so.
No.
Just the units just working out doesn't make it the right number, though, right? So I think just to be clear, you're saying, okay, if we take the surface area of this rod and multiply that by the density?
The density, yeah.
Yeah. No, I don't think that would work. We can try it. This works because you're saying for each... Well, hold on. No, actually, wait, let's see. Well, the surface area would be what? The surface area is 2 pi r... Yeah, 2 pi r times 100. So 2 pi r... R is 0. What was it? 0.15 over 2 times 100. So that's 15 pi, and I want to multiply that by, and that's in centimeters. Yep. So multiply that by 8.92. So I get 420. No, not the same number.
All right. Then.
Not the same number as I get here. Yeah, that wouldn't work. Okay, but there we go. We got the same answer, so it looks good. We're off by 1 somehow, but it's okay. I'll take maybe let's say 15-minute break, and then we'll keep going from here. So this was question 14, so we will continue when I'm back with question 15. Okay. So let me put the screen on.
Could you just scroll up to the question?
Oh, yeah.
Oh, okay.
Yes, I can.
Just 1 second.
There you go.
Okay, yeah, thank you.
Okay, let's say 15 minutes. So back at 7:35, and I'll put that here. Okay, back in a bit. Okay, I am back.
All right. I got a question about the last example again.
Yes.
It has to do with the unit analysis. I just
Mhm.
want to make sure I have it set down properly. So
Mhm.
what you did is, because you chose for the length to be 1 meter, when you're finding the volume, you found the volume per meter.
Yeah.
So that already means meters squared. So then when you multiply it by the density, 2 of the meters cancel out, and you're just left with 1 meter in the denominator, and then the kilograms in the numerator, which is how we're left with the mu.
That's not how I did it. That would be kind of finding, like, if you were finding the cross-sectional area. Because when I did it, I have centimeters. This is in centimeters cubed, right?
Well, yeah, sorry. And then I imagine that you converted the density into kilograms per meter before you multiply it by.
But I left it in this because I have my volumes in centimeters cubed, right? So my volume is in.
Sorry. So let's restart that. So say you find your volume in centimeters, but you found it in terms of the length of the rod being 100 centimeters. So then once you're finding the volume, one of the meters that you selected, which was the 100 centimeters, it cancels out, and now you're just left with centimeters squared, right? Because you found the volume per 100 centimeters.
Oh, what? Okay. Yeah. Volume,
analysis, right? So volume is centimeters cubed, and then because it's per 100 centimeters, the per means in the denominator, and now you're just left with centimeters squared, and then you multiply that by the density.
Okay. Yeah.
So is that the right way to visualize it, or
that's not how I did it? That's not. But I think that would work just as well. Yeah. How I just think about it is that, okay, our mu is the mass of 1 meter of rope divided by 1 meter. So I'm finding the mass of 1 meter of rope. That's the whole point. I need to find this mass of 1 meter of rope. So to find the mass, I know I'm going to have to multiply the density times the volume, right, in order to find the mass. So I find the volume like this. And I have the density, so I find the mass, and that's the mass that's going to go. That mass is the one that's going to go up there in the formula. And then I just do that. And this should be, per 1 meter, I guess. Yeah, it is per 1 meter. Because I can just say this is a meter now because it's just mass on the top. It's not like mass. What I get out of this is not mass per centimeter or something like that. I get mass out of this, right, here. And then this is in grams, just to be clear. Well, that's gonna look confusing now, but yeah, mass. And so then I can just take that number and stick it over 1 meter, and then it just turns into that number.
I see that. All right.
Right. So it's just that, and then I just use it here to solve for t. Okay. Any more questions about that one? I think we're good. Hope so. Next one is number 15. This was 14, right? Next one is number 15. So number 15. So this is rate of energy transfer. This is practice for 16.4. So we're going to go into rate of energy transfer. So transverse waves are being generated on a rope under constant tension. By what factor is the required power increase or decrease if the length of rope is doubled and the angular frequency remains constant? Okay. Transverse waves are being generated on a rope under constant tension. Okay. It's required for the power increase or decrease. Okay, let's find the formula for power first. So power is 1/2 mu omega squared a squared v. So the length of the rope is doubled and the angular frequency remains constant. So this is the power initial, is that. The power final is 1/2 length of rope is doubled. So would this be mu over 2 then? If the length of rope doubles, then, but the mass of the rope, I suppose, stays the same. So then mu would be half of it, and then angular frequency remains constant. So all that changes is a half. The difference is, so by what factor is the power required to, so the power decreases by a half. Or decreases by 2. This is 15. A says 1. So it's no difference. So I guess this wasn't right what I said here. The amplitude is doubled and the angular frequency is halved. Yeah. Let me see. Okay, so I guess this wasn't right what I said, where I would divide the density by 2. Okay, I guess that doesn't really make sense. The density of the rope would stay the same. If it's the same rope. You're just increasing the length. But the density of the rope still kind of feels like that should be split in half. But the idea is here is that none of these things are affecting it, so pi equals pf. So that's that. And then for part B, the amplitude is doubled and the angular frequency is half. So again, pi, I don't want to write it every time, but here, I'll just copy and paste it from here. So pi, just p, oh. OneNote's being annoying? Yes, it is. There we go. So pi, oh, come on, switch to black, please. There we go. Is that, and then pf, okay, what's pf? So 1/2 mu, okay. The amplitude is doubled, right? The amplitude is doubled, so it's 2a squared, right? The amplitude is doubled, and the angular frequency is halved. Omega over 2 squared v. Right? So let's see how this compares. Well, this will cancel, right? Because it's going to be 1/2 mu omega squared a squared 2 squared over 2 squared v, right? Because those are just going to cancel. Or maybe I'll make it a little bit more clear. This is going to be omega squared over 2 squared a squared. So these will cancel, and we're just left with pi. So by no factor again, the difference is 1 here. So it's increased and decreased by a factor of 1, so no difference. And then C is both the wavelength and the amplitude are both doubled. No, both the wavelength and the amplitude are doubled. I read both it twice for some reason. So wavelength is just not here, I guess. So we just don't take that into account. It feels like it should affect velocity, but yeah, we just don't. Since it's not a variable here, we just don't take that into account. Okay, so both the wavelength and the amplitude are doubled, so wavelength doesn't do anything. The amplitude being doubled, oh no, wait, maybe this does do something. For part C. Hold on. Our initial equation is this. Okay, some reason I put a white border on the back, I don't know why, but it did. That's our initial equation. So the amplitude and the wavelength. So amplitude being doubled will put a 2 here, right? We'll put it, or well, 4, 2 squared in the front here. And then the wavelength being doubled, well, v is lambda over period. So this new velocity would be 2 lambda over t. So v over 2? No. That wouldn't make sense because we'd still not get. So the answer, I know the answer is 1. The answer is it's going to be the same again for this one. So we're introducing a 4 by doubling the alpha. By doubling the amplitude, we're increasing it by a factor of 4, right? Because it's 2 squared. But then somehow we also have to reduce it by a factor of 4. Okay, well, omega equals lambda f. Is that what it was? No, that's completely wrong. V is lambda f. Yeah, which is what I'm saying here. Okay, that's not that important. 2 pi over lambda. Huh. Yeah, because I know I can say here, I can just replace V with, oh, it doesn't let me erase for some reason, but I can replace V with lambda over period. And if I double that, it would be 2 lambda over period. But that still is off by a factor of 2. It should be, somehow that should be a 4 there. I'm not really sure. Because my answer would be, right now, my answer would be PF, like the power after, is mu omega squared 4a squared v. Right? So it's increased by a factor of 4. So PF equals 4pi. But that would not be true. I mean, that would not be the answer in the book.
Okay, if you use V equals wavelength times frequency, like that equation, and then the wavelength is halved, you end up with V is equal to V divided by 2, right?
The frequency is halved? No, the
The wavelength is halved, right? For C?
was doubled.
Both? Oh, they're both doubled. That makes more sense. Sorry. Yeah. I was confused.
Okay, so doubled. This is the increased by a factor of 4 is the answer for D. Let's try D. D has wavelength again. So let's see if that makes, so both the length of the rope and the wavelength are halved. So the length of the rope and the wavelength are halved. Okay, let's write that. So I'll copy this again because let's try that. Oops. So for part D, so this would be PF equals, yeah, well, this would just be decreased by a factor of 4 now, because I'd say 1 over 4 a squared v. In this case, if we're if it's the amplitude, what was it again? The amplitude? No, the length of rope and the wavelength are halved. Sorry, the length of rope and the wavelength are halved. So omega, well, no, and I just say this is a factor of 1 because omega isn't here. Is it possible? Let's maybe look this one up because, yeah, let's look this one up quickly. Here. Because the answer in the textbook for C is 1 and for D is 4. So I'm getting C and D the other way around. Is it possible it's just typo? Might be wishful thinking, but let's give it a try. Let's see if that is true. Nope, doesn't let me view the answer for free. See answer. Okay, it's not letting me see the answers for free. It's also not on Slater properly. Unless someone can find it on Slater. Oh, this is not. Yeah, I can't find it. Okay, so I'm not sure. I'm getting this for D, and am I reading it wrong? Yeah, I don't know. Does anybody have? I can find this question maybe. 15 from chapter 16 in Survey. 1114. Yeah. So I get 1141. Okay, well, let's move on for now, but yeah, I don't know. I have a feeling that that's what's
I have a
up.
quick one.
Yeah.
It'll be quick. Can't you relate can't you rearrange the v equals lambda f to be f equals v over lambda, and then that's your frequency, which you can now say w is equal to 2 pi v over lambda?
V over lambda. No, v over lambda.
Right, so if you do now, if you say angular frequency is equal to 2 pi f, you can say that's 2 pi v over lambda.
V over lambda. Sure.
And now you can sub that 2 pi v over lambda wherever there's a w.
So this would be 2 pi v over lambda squared a squared v. And this would simplify a little bit. So this would be 1/2 mu 4 pi squared v squared over lambda squared a squared cubed. So then, and then the question saying the length of rope and wavelength are halved. Yeah, are halved. So this would be, the final would be 1/2 mu times 4 pi squared v cubed over lambda. Well, this would be decreased by a factor of 4, or no, might be increased by a factor of 4. Hold on. Yeah, because this is over 4. Yeah. Okay, so I do get the answer like this, the normal answer. Pi. So I do get the normal. Let's see if we can do that also for C. So for C, we said this. No, I don't want to copy that actually. Let's try C again. Nope, that's the question. So for C, we want to say this. Oops. Okay, whatever. Leave that. And we said omega is 2 pi v over lambda, I think we said. Yep, 2 pi v over lambda. So, okay, actually, I'll just take this equation again, this one, right? That's our simplified p. Wow, OneNote really screwing up on me. There, pi. And now for part C, it asked us wavelength and amplitude are doubled. Yeah, that makes sense. So, yeah, PF would be 1/2 mu 4 pi squared v cubed over, so this would be 4 lambda squared, 4 a squared. Those would cancel, and we get 1. Okay, so v equals pi. Okay, so that's how you do it. That's how you do it then. You make omega equal to 2 pi v over lambda. Why couldn't I do v? Maybe I could have. It seems like equivalently to me, I could have done this. V is lambda over t. Right? Fix that. V is lambda over t. And if V is lambda over t, then wouldn't I just as easily be able to do, but I need it squared. I need the lambda squared in order to make this actually stay equal, but V is lambda over t. Yeah, I'm not sure. But okay, at least this worked. So we got an omega here, and that gave us the answer. Okay, let's keep going. That was number 15, I think. Yep, so number 17 is next.
I have a question.
Yeah.
I wanted to know, like, if you change the length, if, like, the length of the rope is affected, why isn't mu changed?
Well, because I guess because it's the same rope. If it was a different, if they're saying like the density of the rope changed, this isn't like this is like a quality of the rope itself, right? Is like the density of it. So since they're not saying the rope is different, it would be the same mu.
Oh, I thought like mu was like mass per length. So
It is mass per length, but I guess we have to assume that the mass per length, even though the length is increasing, the mass per length stays the same. Because they didn't tell us anything about the mass per length.
Okay,
right?
thank you.
Yeah, no problem. So, okay, so then number 17 is a long string carries a wave. A 6 meter segment of the string contains 4 complete wavelengths and has a mass of that. The string vibrates sinusoidally with a frequency of that in a peak to valley displacement of 15 centimeters. The peak to valley distance is the vertical distance from the farthest positive. Yep. Write the function. Did I get the whole question? Yeah. Write the function that describes this wave traveling in the positive x direction. Determine the power being supplied by the string. Okay. So 6 meters equals 4 lambda, right? Is 4 times the wavelength. 4 complete wavelengths, okay? So I'll say 6 equals 4 lambda. The mass is 180 grams, or I'll say 0.18 kilograms. Then our frequency is 50 hertz. The peak to valley displacement is 15 centimeters. So 2 times the amplitude is 0.15 meters. Okay. And then that's all the information we get. So let's actually solve a little bit. So A equals 0.15 over 2, which is 0.75, right? Yes, that's right. Meters. Nope, sorry, 0.075 meters. I'm going to check that now because I made a mistake. 0.15 divided by 2, 0.075, yep. That's the amplitude. And then our lambda is 6 over 4, right, which is 3 over 2, which is 1.5. 1.5 meters. Okay, write the function now that describes this wave traveling in the positive x direction. So that's going to just be, I guess, not as a function of time. No, as a function of time, I guess. Yeah, I guess as a function of time. So y xt equals a sine, this was k x, positive x direction, so minus omega t plus phi. Yeah, I guess so. They didn't give us anything about a starting condition, though. So phi could be anything, I think. See this. Yeah, they didn't tell us anything about a starting condition. Yeah, so, okay. Let's just go on. So it would be, this would be, so A we said was 0.075. Is that what the answer is? Yeah, okay, 0.075. I was reading the wrong answer there. K is 2 pi over the period. K is 2 pi over lambda. Nope. So K is 2 pi over lambda, so let's solve that. K is 2 pi over lambda, so 2 pi over...
Sorry, just one moment. Where did we, or sorry, how did we figure out that we were moving in the right direction? That's why we had the negative in front of the... There. Oh, okay, cool.
Just tells us in the question, yeah. Okay, so 2 pi over 1.5 is 4.18 or 4.19. Okay, that's our K, so 4.19x. Yes. And then my omega is 2 pi f. Yep, so 2 pi times 50 is 100 pi, so 314. So minus 314, 1/6. T, yep, plus phi. So since they don't give us any information for phi, did we use everything here? Yep. We didn't use that, but we'll use that for part B here, so it's fine. sinusoidally with the frequency of that and a peak to valley displacement of that. That's all the information. I think we're just supposed to choose phi as 0. We're just meant to choose it phi as 0 since it's they didn't give us any information about it. So this is the wave, describes that. Yeah, actually, since there's no phase, it doesn't just tell us anything about like a piece of the wave or anything like that. So this is the wave describing that. This is the answer to the question. Any phi, I guess, will do. So now determine the power. So the power. There's any water here. The power is 1/2, like we said before. The power is 1/2 mu omega squared a squared v, which can be lambda over t. Right? So what do we know here? We know omega, a, lambda, and t. We just need mu. So this is where that thing will come in handy, the mass that we know. So mu is, this is a rope, right? Yeah, so it's the mass of rope per meter. So, oh yeah, okay, there we go. So 6 meters, so we can just take this. So so this is going to be 0.18 over 6, right? Because it's mass kilograms per meter. So that in kilograms per meter is going to be 0.3 or something. Is 0.03 kilograms per meter. Okay, and then we can just plug everything in. So the power is 1/2 times 0.03 times omega, which is 314 squared. Oops, squared. A squared is 0.075 squared. Lambda is 1.5. And I can just multiply by the frequency. Times the frequency, which we said was 50. Yeah. There you go. So put a dot there. Okay, so I can just do 0.5 times 0.03 times 314 squared times 0.075 squared times 1.5 times 50. So I get 623.9 watts. Yeah, close enough. Their answer is 625, but it's okay. That's fine. Okay, any questions about number 17? Oh, you know what? 17 wasn't even part of the questions. Well, that was, I mean, it's very related to what we did though, so I think it was a good question. Was not part of the
how did you get the wavelength? 1.5 meters? Is it given?
The wavelength, they said 6 meters has 4 wavelengths, right? They told us here, a 6 meter segment of the string contains 4 complete wavelengths. So 6 equals 4 lambda. And then I just did it from there. Okay. So 23 is next. Yeah, I just read it wrong before. So next, 23 is about sound waves. So let's give this a try. A sinusoidal sound wave moves through a medium and is described by the displacement wave function that, where S is in micrometers, or micrometers, whatever, micrometer is a tool, micrometers, X is in meters, and T is in seconds. Find the amplitude, the wavelength, the speed of the wave, determine the, yeah. So A, what's the amplitude? Well, it's 2 micrometers. I think that might be nanometers. No, I think that is micrometers. I forget what the symbol is for micrometers, but I'll just say micrometers.
No, yeah, I remember that is micrometers.
This is micrometers? Okay, there we
go.
Yeah. So that's it. That's the amplitude. And then what's the wavelength? So wavelength is 2 pi over k. Yeah, 2 pi over k. So for b, lambda is 2 pi over k. So that's 2 pi over 15.7. So that is 2 pi over 15.7. So I get 0.4 meters. Sorry, 0.4 per meter. No, that's the distance. It should be meters. Yeah, it's in meters. Because k is in per meters, right? So it's gonna be just normal meters after that. But anyways, that's fine. And then the speed of the wave. Well, v equals, so I can say lambda f. Do we know a frequency? No. We might need something else now then. Oh, we can just say v equals lambda over t. So we just need to solve for t here. So let's solve for t. T is 2 pi. So t is 2 pi over omega. So that's 2 pi over 858. So 2 pi over 858 is 0.00732 seconds. So v equals lambda over t. So 0.4 over that. So v equals 54.6 meters per second. Determine the instantaneous displacement from equilibrium of the elements of the medium at the position that. Okay. The instantaneous displacement from equilibrium. I just evaluate the function at that time, I think. Seems too simple, but so s of 0.05 and t is in seconds, so 3 over 1,000 would be, because it's 3 milliseconds, so 3 over 1,000. So then this is going to be 2 cos 15.7 times 0.05 minus 858 times 3 over 1,000. Yeah, and I'll just plug that in. 2 times cos 15.7 times 0.05 minus 858 times 3 over 1,000. So I get negative 0.433 micrometers. Do I have the answer for this one? Yeah, I do. Let's check 23. So 2 micrometers, or yeah, 2 micrometers. B is 40 centimeters. That's right. C is 54.6 meters per second, and negative. Yep, that's right. Micrometers here. So we did that, and then for E, determine the maximum speed of the element's oscillatory motion. Well, we can just go back to oscillatory motion, or however you say it, and V. It said maximum velocity, right? Maximum speed. Vmax is A omega. So A is 2 micrometers, and omega is in what units? Yeah, micrometers. Omega is in per second, right? Yeah, per second. So omega was just 858. So 2 times 858 is 1716 micrometers per second. Yeah. Okay. And that's the maximum velocity. Okay. That's number 23. Anybody ask any questions? If they have any questions, just you can ask questions about like stuff I've done before too. You know, if you didn't get a chance to ask your question. Okay, then I will move on. So that was 23. Let's do 24 next, making sure that I'm looking at the right one. Yep. So 24 is here. This is about okay, this is about an earthquake again. So earthquake at fault lines in the Earth's crust create seismic waves, which are longitudinal P waves or transverse S waves. The P waves have a speed of that. Estimate the average bulk modulus of the Earth's crust given the density of rock is that. Okay. So the bulk modulus of the Earth is the density is that. I see. So V equals the square root of the bulk modulus over the density. So we know that the speed is 7. Well, actually, speed is 7,000. Square root of the bulk modulus over, 25,000 kilogram. Well, 25,000. So there we go. This is going to be 25,000 times 7,000 squared equals B. 25,000 or 2,500 times. Yeah, was it 2,500? Yeah. 7,000 squared. So I get 1.225 times 10 to the 11. It's the bulk modulus. I don't have the answer, so I don't know if that's right, but that seems to make sense to me.
It's right.
Okay, good. Sounds good. Thank you. So 25 is next. So 24, 25 is next. You know, I should start stretching out the questions because I won't get confused if we do that. Okay, so 25. So an experiment wishes to generate in air a sound wave that has a displacement amplitude of that. The pressure amplitude is to be limited to that. What is the minimum wavelength the sound can have? And I just want to put something here. They also gave us this at the beginning, just so you can see all the information. They gave us that. I have a feeling it's going to be useful here. So it's just telling us that the density of air is that, and the speed of sound in air is that. Right. So an experimenter wishes to generate in air a sound wave that has a displacement amplitude. So S max is 5.5 times 10 to the negative 6 meters. The pressure amplitude, P max, is 0.840. What is the minimum wavelength the sound can have? So density is 1.2 kilograms per meter cubed. Speed of sound is air is that. So we're looking for wavelength. So, well, okay, let's look at equations here. So I can describe a wave like this. Wait, the P max.
There's an equation for this.
Yeah, what is it?
T max equals PV W S max.
Yeah, I see that here. So P max equals, I lost it now. Yeah, so PV equals S max, then the density times the velocity times omega. And I think what's going to be helpful, we're talking about wavelength. Yeah, we're talking about wavelength here, right? That's what we're looking for. What's the minimum wavelength? Okay, well, that's not helpful because omega is with period. You know, S max, P max is that. Oh, V is lambda over the period, right? And omega is 2 pi over the period, right?
Right. We're given V, right? V is the speed radio sound in the air. So
Yeah, we were given.
Yeah, we were given. Yeah.
we just need to find angular, the W.
Yeah.
Yeah.
So this can
So
this can stay as 343. Is what you're saying? Yeah. Okay, that makes sense. Just leave it. We're given density and the velocity. Yeah, we need to find omega and then omega in terms of lambda. Okay. Well, actually, I think I can just do, so t equals 2 pi over lambda, right? And no. Because what I was trying to do is I say, okay, v equals, it would be omega over k, I think. And then I could say this is times k, and then k is 2 pi over lambda.
Can we just use the same thing that we used before, the 2 pi times v over lambda?
Yeah, we did that up here, didn't we? We did use that. Well, somewhere. Oh, right here. Yeah, 2 pi times v over lambda. Yeah, that's pretty much, I just did that again. So, yeah, let's give that a try. So here we can say P max equals S max rho v, and that's going to be 2 pi over lambda. So now I can just solve for lambda, I'm pretty sure. And that would be the only, yeah, I can just solve for lambda. So it's going to be, well, divide both sides by this. So it's going to be, okay, it's going to be 2 pi S max rho v squared over P max equals lambda. And so I can just plug stuff in. 2 pi S max we said was 5.5 times 10 to the negative 6. Rho is 1.2. V squared is 343 squared over P max, which was 0.884, right? Yeah. This is lambda. That's a terrible lambda. So this is now 2 pi.
Wouldn't you want to put units though?
I'm pretty sure all the units are right. Let's try here without units, and if we don't get the answer, then it will probably be wrong. But I'm quite certain the units will be right. This was 25. Yeah, I got it right. So 5.81 meters equals lambda.
Is this topic covered in the midterm?
Yes.
I see.
It is, yes.
And what section is it in the unit?
This, well, let's see. This 16.7.
All right.
16.7, yeah. Okay. So now that was 25. So next is 28. I mean, unless anyone has any questions about that, of course.
Sorry, what did you sub in for omega again?
This 2 pi over lambda equals. Do you want me to show you where I got that from?
Yeah, please.
So, it was from this. V. Yeah. Okay. So we know V equals lambda over t, right? We also know that lambda equals 2 pi over k, and t equals 2 pi over omega. So are you good so far? These things?
Yeah.
So I can sub that in. So it's going to be V equals 2 pi over k over 2 pi over omega. So that's just going to be omega over k. Right? So V equals omega over k. And now, well, I'm solving for omega, right? So I can say kv equals omega. And now I need another expression for k, which, well, k is just 2 pi over lambda. We kind of already used that once here, which is strange to use it twice, but it did work. So k is just 2 pi over lambda.
Oh, k is 2 pi over lambda.
From the same equation, from this equation here, which we already used once.
Oh, you restubbed it back in. Okay.
Yeah, yeah, exactly. Which is fine, yeah. So okay, so that's 25. Hold on, I have to cough. I'm gonna. Okay, good. So we just did 25, so let's take a look at 28 then. Some other questions. Probably just a couple more questions for tonight. And then tomorrow maybe we'll try, I guess, some midterm questions.
Can you scroll down
Yeah.
just for a second? I just want to take a screenshot.
Yeah.
It's a bit higher.
Up.
Yeah, just the equation I used. Okay, there we go.
Good.
Yeah, we're good.
Okay. So next one we have is 28. Let me just double check. That's actually part of our questions. Yes, it is. So a rescue plane flies horizontally at constant speed searching for a disabled boat. When the plane is directly above the boat, the boat's crew blows a loud horn. By the time the plane's sound detector receives the horn's sound, when the plane is directly above the boat's crew, okay, the plane has arrived a distance equal to half its altitude above the ocean. Assuming it takes 2 seconds to reach the plane, determine the speed of the plane and its altitude. Oh boy. Let's draw a picture. So airplane. I seem to draw a lot of airplanes in this class. So airplane like that, flying. There's a boat here. So it has an altitude h. Okay. V the velocity, so ax equals 0. Right. When right at this instant, okay, the plane is directly above the boat. They blow a loud horn. By the time it reaches it, let's just say the plane's over here when they hear the sound, right? So let's say that's the plane now. Oop, that's the plane now. It has traveled a distance equal to half its altitude above the ocean. So the distance it's traveled is half its altitude over 2. Okay. Assuming it takes 2 seconds to reach the plane. Okay, so it takes 2 seconds. So in other words, this distance, right? So if v equals distance per time, right? Then that's vt, where the t is 2 seconds, right? And the velocity is the speed of sound, which we know the speed of sound in air is 343. 343. So we already know that distance is 686. Okay, that distance is 686. So we need to find the speed of the plane. In other words, the distance over time. Well, we need to find the distance, really. So essentially we need to find the altitude. Yeah. So, okay, the speed of the plane is the distance it traveled in 2 seconds, right? That's the speed of the plane, right? Because it takes 2 seconds, and the distance to travel is that. So, I see a right triangle here, so it feels like the right triangle can be useful. So it takes speed of sound 2 seconds to reach the plane. I mean, if I knew the speed, I would be able to just, I would be able to find the altitude, and if I knew the altitude, I'd be able to find the speed. So Let's see. Let's see if we used everything. Flies horizontally, constant speed, searching for say when the plane is directly above the boat. I'll say when the plane is directly above the boat's crew blows a loud horn. By the time the plane, receives the sound horn, the plane has traveled a distance equal to half its altitude above the ocean. Assuming it takes the sound 2 seconds to reach the plane, determine the speed. Okay, let's take a look here. Let's take a look here. Oh, hold on. It's the right triangle. So h squared plus h squared over 2 equals 686 squared. And we can just solve for h. Oh, sorry, over 4. Yeah. And we can just solve for h. So it's going to be h squared plus h squared over 4 equals 686 squared. So it'll be 5h squared equals 4 times 686 squared over 5 square rooted. Let's see if that works. 4 times 686 times 686 over 5. So I got the height above the ocean is 614 meters. So this was question what? 28? I don't have the answer. Maybe could someone try to find it?
Aren't you finding the speed, not the...
That's okay. I found h first, so it's its altitude. I found h, that's part B. And then just for the speed, well, I can just say that the speed is, I can say, just using this equation right here.
Yeah.
What did I say this height was? 614 over 2 over 2 equals the velocity of the plane. So over 4. So answer over 4. I got 153.4 meters per second equals the velocity of the plane. But I don't know if this is right or wrong because we don't have the answers to this question. Let's just give it, let me just see, I'll try to look it up, see if, just copy and paste it. See if anything comes. No, I'm not getting any answers here. It's the same number. No, different numbers. Okay, well, let's see. I found an answer with different numbers, so in the question, obviously. So that's not very helpful. Okay. I can find it. Yeah.
Process?
No, but they did have pretty much the only difference in that question was that. Oh, here, maybe something here. Sorry. No. Never mind. There. Okay. Now it'll go. Yes, we're right. We're good. It's all good. I found Yahoo Answers.
Yahoo,
someone put on Yahoo Answers. So yes, there we go. These are the correct answers. Good. I'm happy that worked out. So just draw it, see that there's a right triangle, and then do it. That's all it is. And then find this distance. So this distance, I did it by doing that distance equals velocity times time. Right? So the speed of sound in air times the time it took. So I use that here, and then yeah. Okay, that was a good question. 28, let's do 31. Unless, of course, ask me any questions about this. 31, we're moving on to sound intensity. So, stuff like that.
Is this going to be our last example for tonight?
Probably, yes.
All right.
So, I mean, unless it takes like 2 seconds, but yeah. So the intensity of a sound wave at a fixed distance from a speaker vibrating at 1 kilohertz is that. So that's the intensity. So the intensity is 0.6 watts per meter squared. And the frequency is 1000 hertz. Okay. Determine the intensity that results if the frequency is increased to that. Okay, so, well, the intensity of a sound... Oh, I don't have... Oh, this is my formula sheet. Hold on. I have actual notes on this. That's not on the formula sheet. Here it is.
So when it says constant displacement amplitude, that means the volume is maintaining the same. So you know how you use that equation where B equals 10 log intensity of the thing over the intensity threshold? Yeah, so in this case, B would be the same, because that's what it means when it says constant displacement amplitude is maintained.
Oh, okay.
Because isn't displacement so the amplitude of a wave is its volume, correct?
I'm pretty sure.
Right?
Maybe
so
someone
if that's
can,
maintained, then B should be constant.
Oh, I see. Okay, so that's what we're going at
so,
here. That's what we're going for here. So this is the intensity over I naught, right?
Mm-hmm.
So if this is true before and after the initial, we're looking for, what is it? Determine the intensity, the new intensity that results from a higher frequency.
Yeah, so what I'm assuming our first step would be using the intensity that we do have to find B. And then with the B that we have...
find the sound level?
Yeah, that B, right?
Yeah, so you find the sound level using 1 kilohertz, I think, and then you use that sound level to do part A.
But how would I use 1 kilohertz? This is intensity. We have the intensity.
Yeah, what's the relationship between frequency and intensity?
I'm trying to find that in my notes here. I have intensity is power over area. Yeah.
You just use 0.6 for I, and we know I0 is 10 to the power of negative 12, right? So, and then you find the sound level, the B. I don't know what it's, the beta.
Yeah. No,
Yeah, so they want... So what he means is that constant displacement amplitude means that the sound level, the beta, is the same.
Mm-hmm.
Yeah, so it's same as when
then we
it's
have
0.6.
Then we have to solve for a... Okay, so I got the sound level is 117.8 decibels, right?
Mm-hmm.
And so now there's a new intensity. I mean, there's a new intensity at a different frequency, which has the same B. So I know 117.8 equals 10 log base 10 of I over I naught, right?
And the I naught we're supposed to find in relation to the new frequency that we have.
Wait, we find I naught?
Is it?
Sorry, not I naught. Sorry, I meant I.
But
oh, I see what you're saying, Adam. Yeah, how does it relate to frequency?
But I didn't do frequency at all here.
Power. You can use the power because power over 4 pi r squared is intensity.
Mm-hmm. Yeah.
Yeah, and
oh yeah.
S max is like constant, the displacement. So yeah.
So you're saying put that in here? Put this fraction for I in there.
Yeah, also like we're gonna need the equation for power because to put the new frequency.
But power, unless I didn't write it down properly. Power, the equation for power,
it has a bunch of variables, and I don't think we have enough information.
Yeah, and it also doesn't have frequency.
Constant, but you can change W to frequency. If you want.
That's what I was thinking, but again, there's still amplitude and there's still lambda or sorry, not lambda. Omega.
So it says constant displacement, so like S max is constant. But for the density should also be constant because it's the same material. So you only change W squared.
Okay. So then the power is 1/2 and the power is okay. And I guess we go here. We say that P equals I times 4 pi R squared. So the power equation for power is rho omega squared S squared max V times area. We don't know any kind of... What's that area? What is the area of? The area is the area of surface causing the longitudinal motion. Okay. I guess that'll cancel.
Yeah, so what I'm thinking is we could find the ratio of the two intensities, so how they will change. So if we divide the initial intensity, which is what we're given 0.6, divided by the new one that we'll find, some things will cancel out. Considering that if you scroll back up onto the question, we're told that the displacement amplitude is going to remain constant. So that means the amplitude for both intensities are going to remain the same. So we can cancel those out when we're dividing them. And same goes with the area. We're assuming that the area is going to be the same. So the area will also cancel out. If you get what I'm saying. So then
I see what you're saying. Yeah.
So we're just left with the variables that we can find.
So this would be... So I'm going to use this. So the initial power is this. 1/2 rho omega squared S squared max V times area. Or just say times area. Whatever. Equals the initial intensity, which we have, times 4 pi R squared. And I guess I want to... No, I still want to keep that over here. And then I want to write the new intensity. Oh, no. And then I want to write omega in terms of a frequency. So omega is... in terms of frequency is 2 pi f. So I'm going to say that here. Omega equals 2 pi f. So I will write that. I'll say 4. No, I guess I'll just put it in the square like that. So 2 pi f squared. And then so for our new one, we have, so this is for the initial frequency, and this is going to be 2 pi f final squared S.
Sorry, I got a quick question. Is area included in the power equation?
Yeah, it is. It is.
Oh, I see.
Equals IF. So if I divide these two equations, right? I kind of actually want to divide this by this because I want to know how much the ratio from one to the other. So
yeah, it's just because like what I'm looking at. So if you look at your initial intensity and the final intensity,
put it down here.
You have area in the numerator and you also have area in the denominator. So wouldn't those just cancel out?
They would, yeah. So I'm going to divide the top equation by the bottom equation, right? So I'm going to.
But then that would be, yeah. Okay.
Right, divide. So what I'm going to learn is the ratio between IF and II, right? The final intensity and the initial intensity. So what cancels here? Well, a lot of things cancel. That cancels, that cancels. That cancels, that cancels. That cancels, that cancels. Everything cancels, essentially. Except everything cancels.
Yeah, everything.
Except frequencies.
Except the frequencies. The final frequency to the initial frequency is...
But they're squared, yeah. They're squared.
There we go.
Oh, they're squared. You're right. Yeah, they're squared. Initial frequency... final frequency to the initial frequency. And now we can just rearrange this and say II FF squared over FI squared equals the final intensity. So... the initial intensity is 0.6. The final intensity is 2,500 squared over 1,000 squared. So the final intensity is 0.6 times 2,500 over 1,000 squared is 3.75 watts per meter squared. Let's see if that's right. 31. Yes, we're good. 3.75. That worked out nicely. So yeah, there's that. Okay, good. And then the next one is calculate the intensity if the frequency is reduced to that and the displacement amplitude is doubled.
Yeah,
Okay.
sorry. Okay, I'm gonna
Yeah.
have to stop you. So you know for the intensity equation how it's power over area?
Yeah.
What I'm seeing is it's equal to 1/2 of PW squared velocity S max squared. Okay, so I'm assuming that those okay, yeah, I don't have the original power equation written down. So I'm gonna have to write that down. So let
Yeah.
me just take a quick screenshot.
Yeah.
Yeah, okay, we're good. We're good.
And that area is the area of the cross-sectional thing creating the longitudinal motion. Imagine like the bed of a speaker vibrating.
Yeah.
Right?
All right then.
That's that.
Okay.
So we're going to do essentially the same thing here. It's just that less things will cancel. But it's okay. I mean, no. Sorry. Same amount of things will cancel. I just have to write it properly. So if I just write this here again, this is for B. We still want to find the same... Oh, boy. Still want to find the same ratio. We want to know how much does... this is for B. We still want to know how much... calculate the final intensity if the frequency is reduced, so whatever, and the displacement amplitude is doubled. So the only thing here is that S max doesn't quite cancel. Because... Well, they kind of do still cancel. Because the S max here is 2S max squared. Right? So this still does cancel with that. It's just that what we're left with is the final frequency squared 4 times the final frequency squared, right? Divided by the initial frequency squared, well, equals the final intensity over the initial intensity, so the initial intensity. Right, that's the only difference, is that we have a 2 in here now.
What does the S represent again? In the power
S is the
equation?
amplitude. The S is the amplitude.
Okay.
That's the amplitude. So now I can just plug this in. The initial intensity was 0.6 times 4 times 500 over 1,000. Sorry, squared and squared. 500 because the final frequency is 0.5 kilohertz. So 500 hertz, and that'll be our final intensity, which is 0.6 times 0.6 times 4 times 500 times 500 over 1,000. So I get 3/5, which is 0.6 watts per meter squared. And that is correct. And there you go. Oops. Okay. Well, that'll probably be the last question for today, but I'm still here for questions. If people have questions. But
Wait, can you show me where you got the 4 from for the second, for part B?
So I set up the same equation. It's just that our new amplitude is going to be 2 times the old amplitude. And it's being squared. It's being squared here.
Okay. Yeah.
So that turns into a 4. Make sense?
Yep.
There you go. Okay. Okay, well, any other questions? I'll stick around for a little bit. But yeah, that's our last question for today. Hopefully I'll see you guys tomorrow. Yeah, thank you, James.
All right, have a good night.
I just saw that now. Yeah, have a good night. Have a good night. See you guys. Yeah, tomorrow I'll be also doing a live session at 6 o'clock. And we'll finish everything up then and hopefully get to some of the midterm practice questions because I have not done any of those.
Do they post the midterms on the D12?
I don't know, but people have been telling me about midterm practice questions, so I don't know.
Wait, did we finish all the textbook questions?
No, we did not.
Oh, okay.
We still have 9 questions left.
Okay.
From the textbook. Which we can definitely finish tomorrow, but we also want to have time to do our things. Like for some sort of perspective, we did 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We did 14 questions today.
Oh, okay.
Okay, well,
You-
that's everything. Yeah, yeah.
I have like a one really quick question.
Of course.
Can I just post it in the chat?
Sure.
Okay, bet.
Which chat discussions?
The discussion chat. Post it right now. So basically, it's an easy question. I just don't remember how to figure out whether it's positive or negative.
Well, that's not letting me
Using
drag and drop it. There you go. Okay. Oops. Well, hold on. Give it 1 second here.
Okay.
It takes a second for OneNote to start responding. Okay. The motion of a spring mass system is described by that equation. At t equals 0, the position of the mass is 1, and the oscillating velocity is positive. What is the phase constant? So I would solve it like this. Okay, so the position at t equals 0 is 1, so 1 centimeter. That's in centimeters? Yeah, okay. So 1 equals 2 cos phi. Right, so 1/2 equals cos phi. Right. So where does what angle cosine of that angle equals 1/2? Well, pi over 3. So phi equals pi over 3, or right. So where's cosine positive? Cosine is positive here and here. So to get an angle into that fourth quadrant, we do 2 pi minus the reference angle, which is pi over 3. Right. So 2 pi minus pi over 3 is 5 pi over 3. So our other solution is 5 pi over 3. And now we have to decide which one gets us the correct answer, right? Well, we know that the velocity is positive, right? So we want so we can if I take this equation, the x of t, right? So one of these will give us a positive velocity, one of them won't give us a positive velocity.
Oh,
So,
I see.
right? So if I take 2 cosine, it was omega t plus phi. Yeah, plus phi, right? And I wanted to take, well, if I take the derivative, I won't have, no, it'll be a positive. Okay, yeah. So if I take the derivative, it'll be v of t equals 2 omega, negative 2 omega sine omega t plus phi, right? And I want the velocity at 0 to be just a positive number, right? I want this to be a positive number. So negative 2 omega sine phi, right? So essentially, if I want this to be a positive number, I want this to be a negative number.
Oh, okay.
So sine of which of these angles gives me a negative number? Let's give it a try. Sine of
You don't need a
pi.
calculator to see it from the thing.
Yeah, that's true. And so it's going to be 5 pi over 3, right? So that means that phi, we want it to be a positive, so it's going to be pi over 3. Sorry, pi over 3 is the one that gives this. Never mind, I'm confusing myself now. We want this to be negative, so this is the angle that makes sine phi negative, which makes the velocity positive. So that means that phi equals 5 pi over 3.
Which is also equal to negative pi over 3?
Which is also equal to negative pi over 3.
Okay. All right.
That's correct.
Yeah, I mean, you could also think of it as if you were to put negative, like the incident angle, pi over 3, you just put a negative in front of that.
Yeah, that works for cos. That works for, that works for cos.
Oh. Yeah, both ways work. That's true.
Yeah. And that would, this, what we're just saying is that this equals negative pi over 3. So you can just think of it like that. Oh yeah, which is the answer in the book. Yeah.
Okay, thanks.
Okay. No problem. That was helpful.
Yeah, I'm gonna be honest. I'm kind of procrastinating studying PCS
Yeah.
So where'd you get all your formulas from? Because I kind of want to go through the textbook, but I feel like it'll be too long.
Well, go to homework help and look in pinned. I have my formula sheet and my notes there, so you can go look there, right? And you can find everything.
Yeah, that's what I was gonna ask. Like, did you get all the formulas, or
Yeah.
did you just?
The formula sheet doesn't have everything relating to sound waves. There's more to it. Like there's no decibel stuff on the formula sheet, which I have to add. But in my notes, there's everything, which is like longer.
Okay.
But my notes has everything.
Yeah.
Everything up to Doppler
All right.
effect, including Doppler effect.
All right, perfect. Thank you.
No problem.
Adam?
Yeah?
I sent something relating to question 7 earlier, but I don't know like if it really is relating, and like I don't think we solved that one.
Yes, we didn't solve that one. I'll just put question 7 here again. Let me find it. Question 7 is this one. Nope, doesn't want to put it. No, now it does. So you said here, okay, question 7 by graphs the two equations on Desmos. The difference between the 2 points at x equals 0 is 6 point. Oh. Yeah. The difference.
So like maybe it was just, maybe it was just saying like, on the equation, the wave equation given in the question, when a particle there is at the origin, like how far is it away from a wave that's displaced by pi over 3, but I'm not sure because like it gives the answer that way, but I wasn't sure if that's like right or...
No, that makes sense. That makes sense. We have a wave, and the question's asking, for this point on this wave, imagine you had another wave which was out of phase by 60 degrees, right? What is this distance? What is that distance? That's essentially what it's asking. Right? Which is what you found.
Yeah. So I think that was...
Yeah, so then we just say, well, we're solving for x at, I guess just set t equal to 0. And we know y is 0. How would you solve for the... Yeah, you'd have to set t equal to 0. So we'd say 0 equals 0.15 cos 15.7x, and solve for x here. Okay, let's do it. So 0 equals cos 15.7x. So cos inverse of 0 is pi over 2. So let's just say pi over 2 equals 15.7x. So x equals pi over 2 divided by 15.7. So I get what you said. Yeah, okay. I get the first value is 0.1. That's the x value of this point. That's there. So we're kind of disregarding the origin thing by saying this. We're just saying, we're not saying x equals 0. We're just saying y. Well, let's get the answer first. And then similarly, I have another graph, 0 equals 0.15 cos of the same thing, but we're just out of phase by pi over 3, right? And so I would get the same thing at the end. I'd say pi over 2 equals 15.7x plus pi over 3. So pi over 2 minus pi over 3 over 15.7 equals x. So pi over 2 minus pi over 3 over, answer divided by 15.7 is 0.0334. So what's the difference between these 2 points? Or the distance between these 2 points? In meters, I guess. Is this in meters? It doesn't actually give us any units here, so I don't know why they're giving us meters. But anyways, what's the difference? Well, I guess I would do 0.1 minus 0.0334, which 0.1 minus the answer is 0.0667, or well, actually 0.0666. But that is the answer in meters, which is 6.66 centimeters, which is the answer. So that's all it is. The origin thing, I guess, is what was screwing us up, right? The origin.
I think I think the origin thing is just to say set t equal to 0 in both equations. I think it's just a confusing way to say that.
Possibly, yeah. But thank you for that. Thank you for looking into that. Yeah, that is the answer. That's good.
Can you recap what you just did? Sorry.
Yeah, essentially, I just took this green graph is y equals this, and the golden graph is this, right? So I just solved for when this is equal to 0, right? And I found the x position of when it's equal to 0, this first little bit right here. And we're asking for the equivalent point, right, on this graph. What is that x position? Well, we got this. And what's the distance between them?
Okay, I see. Makes so much more sense.
Right? Yeah, that does make more sense. Just weirdly worded question, but I'm happy we did actually figure that out. Okay, well, any more questions? If not, I am done for today.
Would you mind taking a look at this? If it's like too much, then we can just leave it for later, but I'll post some discussions.
Possibly, yeah, let's take a look.
Oh, and I couldn't wrap my head around it. It was driving me crazy.
Let's see.
Oh my god, same.
Yeah,
It
no,
took
you
me
don't
so
understand.
long.
It was like matching my head against the desk.
So a steel of length, so I guess a steel rod of length 50 meters, and copper wire of length that, both with that diameter, are connected end to end and stretched to tension of that many newtons. How long will it take a transverse wave to travel the entire length of the wire? Transverse, okay. Model the wires as cylinders. The volume density of steel is that the volume density of steel. So we're trying to find the speed. Well, okay, we need to find the speed of the wave through that, which is just the tension over the mass density. Well, the mass density, we know the tension. Well, we need the speed to find this, we know the length of it, right? And so we can, if we know the speed and the length, we can find the time it takes to travel. Well, the mass density is the mass per meter, right? But we have 80 meters. So we want to know how much mass is that. Well, the mass is going to be 50, so the mass of steel is going to be 50 times 8,050. The mass of the copper is going to be 30 times 8,960. We'll add that together and divide that by 80, and that'll be our mu, right? So 50 times 80, 50 over 30 times 8960. So that answer, oops, no, I wrote that wrong.
Wait, how would that?
I
Sorry,
said,
how would
I
that
said
get
it
you?
wrong too. Yeah, sorry.
How would that get you mass? Because isn't it kilograms per mass cubed, or meters cubed, and it's just 50 meters, right? Right.
What? This is. Oh yeah, you're right. Sorry, hold on. This is yeah. That's not what we want. We want the
volume,
area.
right?
We want the volume. So we want the area. So they both have a 1 millimeter diameter. So we want the area of the face, which is pi r squared. So the r is going to be 0.001 over 2 squared. Right, that's the area of the face. We want to multiply that by the length, which is 50 for the steel, and multiply that by 80/50.
Okay, yeah, okay, that makes more sense. Yeah.
Pi 0.001 over 2 squared times 30 times 80, 89, 60. Take those
You just
two
want
values.
the answers? I
Yeah.
already did them.
Do you have them? Okay, what is it?
Yeah, for steel, it's 1.264 kilograms. And for copper, it's 0.819 kilograms.
Okay, thank you. So 1.264 plus 0.819. And I'm going to take that value and divide it by 80. So now our mu is 0.026. So now I can find V, because V is the tension, which is 150 newtons, over 0.026. So the square root of 150 over 0.026 is let's just say 76 meters per second. And now that we have that, well, the distance, the total distance is 80 meters. The velocity is 76 meters per second. Velocity is distance per time, right? So time is distance per velocity. So 80 over 76 is 1.05 seconds.
Is that the correct answer? Let me check real quick. Give me a second.
Yeah.
It's 0.53 seconds. I got the same answer as you too, Adam.
Okay.
Is it the same velocity for both parts though? Like, does it not go at a different velocity when it hits the copper wire?
Yeah.
So wouldn't U be different for each part?
Okay.
And then you
Yeah.
calculate it that way?
Okay. So
I don't know,
let's say velocity in the steel, but the tension is always 150. The tension is always 150.
Yeah,
So
because that's spread evenly throughout the entire run.
So then mu for the steel is just going to be 1.264 over 50. 1.264 over 50, right? So that's going to be the square root of 150 over 1.264 over 50. So that's 77.03. And I'm just going to say the the time is, what was it? Distance, so 50 meters over 77.03. 50 over 77.03. So this time is 0.665. Hold on, that's already bigger than the answer, isn't it?
Oh, yeah.
Right.
I don't understand though. Like, what am I doing wrong?
Do you know that that's the right answer?
Wait, let me
It
check
says it is
again.
on the D12 website.
Could it be a typo? Because I did it like 2 times and I still got 1.05.
No, man, it's Ryerson who knows if they're making a typo or not. I don't know. I really don't know. There's like no way to verify for me. I could Google it, but
Yeah.
if not, it's okay. Like, more or less, we know what we're doing at the end of the day.
Yeah, we do.
It's just a bit aggravating that we're not getting the answer.
These tutorial problems are nowhere on the internet. Like, they're nowhere.
They're not,
I looked
yeah.
so long.
I guess then they write them for the tutorials.
Yeah, I found it, but it's behind a paywall, so that's always fun.
Yeah.
Check this one.
I mean, yeah, you have to pay. Like, a lot of them you have to pay.
Let's see if I can work around it.
Yeah, if this doesn't work, I don't.
Yeah, it's fine then.
Another way.
Yeah.
No, it's a
check
good
it.
question. It's a good question.
Yeah.
Where'd you get it from? The tutorial, you said?
Yeah, tutorials.
And there's no tutorial solution?
No, it's just a straight number, which is also very aggravating.
Yeah.
This is still tutorial 3. I haven't even done the next tutorials.
Yeah. I have not done any tutorial practice.
Yeah, I
per se,
haven't
so-
done. Yeah, no, yeah. I